Alright, so I'm just testing to make sure the audio is working correctly. Looks like it is working correctly. Alright, because every Wednesday I have to move my setup to a different location, and the usual mic that I use is no longer uh, here, so I have to use a slightly different setup. So, and that's why I need to test it. And for today's lecture, I think I'm going to turn off the webcam because I might need the entire screen, so that's why I'm going to turn it off. There we go. Alright, so I can see the Discord messages, and we're going to stay in free playing, for the most part today. Free playing is a new tool, but I find it, well, let's try it, okay? Because I've never tried to explain these recursive functions using free playing, and I think it might be a very good tool for doing this sort of stuff. So we'll see. We got another minute before the class starts, and I believe this is the problem that I said I would solve from Monday's class. So if you had a chance to work on this already, you can kind of compare your solution to mine. I can see my mic is clipping a little bit. Let me just kind of change the gain a little bit so it does not clip anymore. Alright, so that should do it. Yep, doesn't seem to be clipping anymore. There we go. And let me check the streaming side, the live stream. Yep, that's working. So I'm going to close that window. We got 5 more seconds to go. And there we go. All right. So what we're going to do today is to take a look at the two functions. Basically, they are mathematical definitions, but it will be pretty easy to turn them into subroutines. And let me go back to the web page. So this is what we are talking about. This is omega. Omega is used to generate the actual set of permutations. And then later on, we'll also have the U function, which is used to generate the combinations instead of permutations. Now, I do not claim that any one of these algorithms is very efficient, but it gets the job done, and it is basically looking at things from the perspective of math. So let's go ahead. Now, if you have any questions, just type it in the text channel. I can read the text channel on the side. It's interesting how you don't realize a 1080p monitor, is not really, doesn't have that many pixels until you try to do a live stream along with a Discord on the side, and then you quickly run out of pixels. It's just kind of interesting. I never realized that. Alright, so this is what we want to figure out. What is omega 2 of the set ABC? In other words, if the initial outcomes for the first trial are A, B, and C, and ordering is important, and we have 2 trials, what are the possible outcomes in this case? That's basically what the question is asking. So the way we figure this out is we go for we're looking up the definitions here. And for omega 0, this is the end of the recursion. Ordering is important in permutations. That is correct from the text channel. So we know the end of the recursion is when we have omega 0. In other words, we have 0 trials, and whatever t is, it doesn't matter. It can be an empty set, it can be a set that is not empty. It doesn't really matter, because when we have 0 steps left, then the sequence that we can get out of choosing items from the set is going to be an empty tuple. It is not an empty set. It is an empty tuple as an element inside a set, because omega is a set to begin with. On the other hand, if we're dealing with anything other than omega 0, then we have to go for the general case, which is what you see here. And the way it works is omega I of t, which means we start with t as a set, and we have I trials in this particular experiment, and we are going to make a big union out of just pick E out of the set T, and this is basically a loop saying for each E in T, do the union thing. And the items that we are doing the union together is everything from the open parenthesis here and all the way to this end parenthesis here. So E itself is used to make a set, because unless we have a set, we can not use Cartesian product. And then the next item that we are using on the other side of the Cartesian product is omega I minus 1, which means we have an experiment that has one less trial. And the set that we can choose from is also going to be a little bit smaller, which is t minus e. And there's a question in the text channel. What exactly is the big U called? You can call it the outcome set. It is the outcome set of experiments when ordering is not important. I just don't want to use omega again. That's the only reason why it's called U. Oh, you mean the big U over here? Yeah, the big U is basically just a union of a series of expressions. It is analogous to the sigma for summing and the big pi for product. There we go. Yeah, it was my misunderstanding, not yours. Okay. So yeah, the big U is basically just a big union of all the items in the expression. Is that okay? Did I explain it sufficiently? Okay, excellent. Yeah, once we actually work out this example, hopefully the meaning of the symbols would also be cleared up. All right, so what we're going to do is not worrying too much about the U, but we do want to know what E is being chosen and what the recursive call is going to look like, in omega I minus 1. And then we have another question for omega 2. How did you go from the first part to the second part? Well, we are still working on the first part. So this is what we want to find out. And then what we want to do is to find out what the subparts, the three subparts that we have to figure out. Okay, so I'm going to work out the subparts here. Now, once again, if you have any questions, just go ahead and ask. So the first subpart, okay, I'm going to use LaTeX for everything, so it looks good. So we are going to say, we are going to bind E to A in the first case, and obviously this is a little bit too small. I have no idea why this one looks big. Oh, that's because it is at a different level of the nodes. Okay, that's fine. I'm going to just have to zoom in a little bit here. At some point we might need to zoom back out again. Alright, so this is one, and I'm going to duplicate this one so that because the next one looks about the same, except it's going to be B, and I just want to see if there's a quick and easy way to clone a node. I suppose I can copy and paste. Okay. Yeah, okay, that works. Copy, paste. Oh, okay, it's pasting it to the wrong parent. Okay, that's fine. And then we're gonna paste one more time, but choosing the right parent this time. Okay, so copy and paste. Nope, that doesn't work. Huh, that is strange. Alright, so let me change change all of these expressions first, and then I'll go back to the text channel to answer any questions. Double click. Alright, so I'm looking at the text channel. Yeah, so we start with omega 2. There's no omega 3 in this case. We are starting with omega 2, just basically to illustrate the fact that, oh, I see. It's pasting on the other side, which is not what I want. That's okay. Well, we got everything we need already. Okay, so getting back to Jonathan's question, I just want to try one particular example where the number of items in the set is more than the number of trials. I mean, once we can work this out, obviously we can also work out what omega 3 is going to look like. So, so Armand is correct. Okay, so now what we do. So basically, this is a loop. Okay, let me go back to the notation here. So basically, this is basically a loop that says for each element of t, do the following, and then whatever the following is an expression, and then we take those expressions and then form a big union at the end after we figure out what each expression is going to be. So the first part is easy because in the Cartesian product, the first one is really just the set of E by itself, and we already see that in the 3 iterations, the first one is when E equals to A, E equals to B, and then E equals to C. So these 3 are representing 3 iterations of the loop itself. So are we understanding why we have these 3 items here? They will be expanded. It's just that I want to make it very obvious what E is. It's basically just an iterator to go through all the elements in the set. No, E is not trials. E would be representing the outcome, the actual outcome of the first trial of the 2. So this one is basically saying, what if in the first trial we end up choosing A? What if in the first trial we end up choosing B? And what if in the first trial we end up choosing C? So that's what these 3 expressions are trying to convey. Yes, Jonathan is correct because at this point the bag has A, B, and C in it. So the outcome can be A, B, or C for the first trial. So now what we're going to do is to expand it so that we figure out what is omega I minus 1 of this particular set here. So we're going to expand this particular expression, and then we'll say we need to figure out, okay, what is E. Oops, I need to use a backslash because otherwise the braces are absorbed by LaTeX itself. So we have this, and then times, which is the Cartesian product symbol. Okay, right. It doesn't seem to let me type in it. Okay, let me click OK, and then go back in to type some more. Oh no, that doesn't look good. There we go. Yeah, the problem is the keyboard on my laptop computer itself has a bounce issue, so it just kind of sometimes it would do a double tap of a key. Alright, so now we have the Cartesian symbol, and then we now want to figure out what is omega. So with the first iteration, which is what we are editing right now, the element A is chosen to be the outcome of the first trial of the 2, so it is no longer available for the second trial. So for the second trial, we only have B and C left in the set. So so this is basically what we are trying to figure out, which is E, and then we have a Cartesian product with big omega. I forgot about the subscript. So the subscript is now 1 because it is 1 less than the current number of trial. So this one is trying to handle 2 trials because the first trial has already selected its outcome. So what we need to do is to figure out the sub-trial, basically the rest of the trials. In this case, the quote-unquote rest of the trials only has 1 single element. It only has 1 trial left, but it has 2 elements to choose from. Yeah, so it's going to look like a tree, but I'm using this notation so that it is, so it's easier to visually see, how everything works out. So this time, we have okay, I think it's probably better to instead of using the name of the variable, we're gonna just use the element in here, and then we have times, and then big omega subscript 1 of, this time B is chosen in the first trial, so we have A and C left for the second trial. There we go. And I'm going to go back to fix this one because I don't want to use refer to the variable. I want to refer to the exact element that we have chosen in the first trial. So in this case, the first trial has chosen element A, and we're going to do something just like it's the same thing here. So I have a lot of editing to do, just because I'm repeating all of these things along the way, but that gives you a little bit more time to understand what is being represented in this notation, in this particular mind map. So this is big omega of 1, and then the set only has A and B in it because C is the element that is chosen in the first trial. There we go. Alright, so good to see there's a thumbs up. Okay, and Jonathan is typing. Exactly. This is basically T minus E, or E in curly braces, because once you have chosen C to be the outcome of the first trial, it is no longer available to the sub-trial, or the sub-experiment of omega 1. So that's basically what it is. Alright, so now we have to figure out these two. Okay, so our subproblem is now, what is omega 1 of BC, what is omega 1 of AC, and what is omega 1 of AB. For the red one, because E is A, so that's why ABC minus A. Now, when I say ABC, I mean the set of ABC. When I say minus A, it means the set of A. So that only has B and C left over. Okay, very good. All right, so now what we need to do is to figure out what is omega 1 of BC. So as we try to figure out what is omega 1 of BC, we are basically using the same approach, and we form an iteration. This time the iteration will iterate through E equals B and also E equals C. So there we go. Let's go ahead and do this. Oh, what did I do? Okay. I was trying to hit the insert key. Oh, there we go. It's the keyboard is different too. When I use the laptop itself without my external keyboard. All right. So in this case, the first iteration is when E equals to B, and then the second iteration is when, oops. As you can see, my keyboard is double tapping when it's not supposed to. So it's gonna increase the amount of time it takes in order to type something. Alright, so in order to figure out what is omega 1 of BC as a set, it has two iterations, because now there are only two things left in the set. The first one is when E equals to B, and the second one is when E equals to C. But this is not telling the entire story, because now we also have to perform the recursion, because I does not equal to 0 at this point. We don't have the base case yet. So what we now need to figure out is what is B as a set, Cartesian product with omega 0 of the set that has B removed. So we are looking at BC minus B, so we only have C left in the set at this point. Alright, so can everybody understand why this is the next thing that we need to resolve? Basically, this thing here, B in a set times omega 1 of C, is what omega 1 BC is going to look like. Well, that and also union with this case. Okay, very good. Alright, so we're going to work with this case, do some editing here. So now we have C as a set, Cartesian product with big omega 0 because we have 0 trials left. And since originally we had B, C as choices, but in this particular instance we have chosen C to be the outcome of the second trial, so that means we only have B left. Now obviously in this case, since we don't have any trials left, whatever is in the set doesn't really make a difference. Alright, so what did I do wrong? Omega. Omega. Did I misspell omega? That's supposed to be a backslash. There we go. Okay, so I did use the vertical bar because I guess I accidentally clicked the shift symbol. There we go. Alright, so now we have one more level to go because omega 0 of C is a base case. So now we don't have to perform another recursion, but we do want to kind of express that because based on the notes, the base case is, oh, this is really just a set of an empty tuple. So we're gonna put it here, and we'll let's see, we're gonna insert here. So we'll go ahead and insert one more time, and this boils down to something that has no recursion because this is basically just the set of an empty tuple, like so. Okay, and the same thing for this one because it is also trying to resolve omega 0 of something. So you can probably imagine this one is going to look kind of like this, except we have AC instead of BC. This one is kind of like these two, except we have AB instead of BC. So let me see if I can multi-select. Nope, doesn't seem to let me do that. Okay, can I shift? Oh, okay, I can. I'm trying to, there we go. Alright, so now I just have to quickly go back in and edit a few items. So this one doesn't have B. Instead, all the B's should be A's. Alright, so since I'm doing all the mundane editing here, it's quite interesting that FreePlane as a tool is very scriptable. So it is entirely possible for me to script this whole thing so that it becomes, I just need to run the algorithm or click a button so it would automatically generate what you're seeing here. That is entirely possible. I just have not had the time to figure that out yet. Alright, so this is AC, so this one needs to change too. And that would not be C anymore. That's going to be A. And yep, that looks good. And then we're going to change this one. So this has AB. So I'm going to keep the B and change this one. Change one of the B's. We'll change the first B, I guess. Okay, so when E equals to A, then we have A at the set of A Cartesian product with omega 0, in this case of B. There we go, and then fix this one so that we only have A left. There we go. Alright, so let me just double check to make sure that everything looks good. So we got BC, we got B and C here, and then C and B here, ACCA, and then ABBA. So I believe everything is looking good at this point. Alright, so we got some questions in the text channel. So for instance, we have A for step 1, which is the first trial, and B for the second trial. There's no third step because it's omega 0. So omega 0 doesn't really do anything because all it does is to return a set of an empty tuple. That's all it does. Because at that point we have 0 steps left. And when you have no step or no trials, then you're not going to select anything. Yeah. Alright, cool. All right. Nope. Omega 0 always gives you a set that has an empty tuple because that is how it is defined. So when you look at omega 0, this is how omega 0 of t is defined. It doesn't care what t has. It simply returns a set that has an empty tuple. Exactly. We only have two trials. There's no third step. The third step is basically just a terminating step saying that, oh, okay, we just ran out of trials. Let's get back. That's basically what the quote unquote third step is trying to do. Omega 1c is just, well, it is a tuple of c, not just c. It is a set that has c as the only item in a tuple. So I'm going to type in the text channel just so that I can respond to that one. The answer is a set that has one single tuple where inside the tuple there's only c in it. All right, so Aman is saying, so it has omega 0. Yeah, it doesn't matter what set you're giving omega 0 because omega 0 says the 0 is saying we have no trials. So it doesn't matter how many items or no items in the bag. When you have 0 trials, you're going to return empty-handed. And that's what the empty tuple is representing, is quote unquote empty-handed. There's no, well, I mean, E is the iterator. E is the one iterating through the loop. But when we have omega 0, we don't bother to iterate anything because we don't really even care what T looks like. Exactly. Omega 0 is a base case. It just simply returns this fixed result here without looking at T at all. Yep, that's one way to look at it. We don't have a loop, but we do have a recursive definition that has to stop at some point. Okay? So this example is actually useful. Hopefully, it is also useful in your CISP430 class, because your CISP430 class probably have to deal with quite a few recursive algorithms. So this is kind of one way to visualize your recursive algorithm, is to basically look at the bigger problem. The big problem says, oh, I can break into smaller problems. 1, 2, and 3. Now, at some point, we have to combine the solution of the 3 smaller problems, but we'll deal with that later. And then for each one of the smaller problem, we break each one up into even smaller problems, like so. And then for this even smaller problem, it just has an answer right away. It doesn't perform recursion anymore. So now we are at a point where we can go back and say, oh, okay, we know exactly what we need to do now. Okay. Alright, so what I'll do is now we are taking the return value, which is this thing here, and then use it to substitute the omega 0 of this portion here, so that we can actually perform the Cartesian product. So now we go back here, and then we, let me see, what is the easiest way to do this? Okay. Alright, so I'm just going to do a copy and paste from here to here, and then I'll replace omega 0 with the value of omega 0, which in this case is the set that has an empty tuple in it. Alright, so we're going to take a look at this first before I go any further. Is that okay? Does everybody understand what we have here? Okay, very good. And I'm gonna, open the floor just to make sure that everybody has enough time to think about it. And if anyone has any questions, go ahead and ask the questions. I'm just gonna check the private channel. Nope, nothing from DM, so that's okay. All right, so we got a few questions coming in. Very good. Yes, we just stopped the recursion because we have hit a base case. Well, the reason why omega 0 is a set that has an empty tuple in it has to do with what it means. Because that 0 is basically saying we have no trials, which means we are not allowed to choose anything out of the bag. We are not allowed to pick anything out of the bag. So if you ask me, hey, Tack, why don't you not pick anything from the bag and show me what the result is, then I'm going to show my empty hands. It's like, okay, I'm empty-handed because I'm not allowed to choose anything from the bag. And that's what the empty tuple is representing. Basically we came back empty-handed. And with permutation, because ordering is important, that's why we use tuples to represent the outcome of experiments. Alright. And math returns 1, so we need some element in the set. Not really sure what that means. A set is really just a value. It's not a numerical value, but nonetheless, it is basically a value. So I'm going to extend this and perform one more step, because now we can look at the actual Cartesian product, and then I will say, okay, we just end up with a list that has B in it. Okay, and we'll take a look at this and see whether we are convinced that this is the result. So when we make a Cartesian product between a set that has a singleton item, which is B in it, and the other one has a singleton item, which is an empty tuple, we just end up with a tuple that has B in it. This should generate some questions because there are two ways to interpret what the answer is supposed to be. It depends on whether we can nest tuples or not. So in this case, I'm saying that we cannot nest tuples. So when you are making a Cartesian product where both sides have tuples, you are concatenating the tuples to make a longer tuple. Are we doing okay so far with this? Is everybody okay with the set of just B in it? Cartesian product with the set with just an empty tuple in it would become, the set that has B inside a tuple by itself. Are we okay with this outcome? Okay, very good. So one way to look at an empty outcome, yeah, sure, think about it. So one way to look at an empty tuple is it is just an empty array. It is still an array. It is an object, but it has nothing in it. It is a container that has nothing in it. Kind of like an empty folder. But an empty folder is still a folder by itself. It still has an existence. Exactly. So Jonathan, that's exactly what I said, why I said what I said. Okay, let me say that one more time. This is exactly why I said what I said earlier. So whether this is the right outcome or not depends on whether we look at it as whether the tuples can nest or not. So I'm basically saying when you have nested tuples, then you basically just want to flatten everything so it becomes just one level of tuples. Exactly. Let me make it even more clear. I can make it more clear. So it becomes a set, technically speaking, with B and an empty tuple as the second thing originally. But I am simply saying that it is when we flatten this, which is a tuple with B and an empty tuple in it, when we flatten it, which basically means we are removing all the hierarchical structure from it, then we end up with just a tuple with B in it. No, you're not slow. It's just that these concepts takes. We are looking at some kind of strange way of applying what we have learned about Cartesian product. Because when we first talked about Cartesian product, we never talked about what if we have an empty tuple on the other side? So this is what happens when you have an empty tuple. Basically, you're flattening the structure. It's kind of like, the concatenation between a string and an empty string. It is not becoming a string and then with a string that has an empty string in it. You basically just end up with the original string, because when you concatenate a string with an empty string, you're just concatenating the two. So there's no nesting whatsoever. Okay, very good. All right, so I am going to work with this one, but this time I'm not gonna, expand it all the way out. And all I am going to do is to say that this ends up as a set that has a tuple with just C in it, like so. And I mean, the reasoning is the same, and that's why I'm not expanding anymore, and I'm just giving you the answer here. So this one just has A in it, and this one has C in it. And I'm going to be a little lazy. I'm just going to copy this so I can paste it to all the other ones, like here. Paste. And this one has A, and this one has B in it. Alright. Alright, so I'm going to pause a little bit here, just so that I can visually double check to make sure that everything looks right. But you can think about what we have already done up to this point, and then once we are satisfied with the results of omega 1 of BC, the result of omega AC, and the result of omega AB individually before we do the union, then we'll go back and process the top level function call. So at this point we haven't done any union yet. Okay, at this point we have just looked at the components of omega 1 of BC, but we have not actually performed the union of those components yet. Right, so at this point we have figured out what is the set of B Cartesian product with omega 0 of C, and that end up to be just B in a tuple and that itself in a set. But this by itself is really just a one of the two components of omega 1. So we have not figured out the entire omega 1 yet. We have figured out the two subcomponents. One is this one and one is this one of omega 1 of BC. And these two are components of omega 1 of AC, and these two are components of omega 1 of AB. But we have not combined those two yet. Alright. Okay, so now what we need to do is to insert one more level of nodes, because we need that one extra level to do the combining of these two. Okay, or I can just write it here too. That's the other way to do it. Let me see which way is better. I think I can just write it here, because omega 1 is the union between this set and this set here. So let me do it first like this, and then see if you guys are okay with that. Okay, if you're not okay, then we'll go ahead and extend it a little bit. Alright, so I'm just going to copy this and paste it here, except I'm going to replace omega 1 of BC with the following. Okay, it's going to be the union, so we're going to have a cap. No, this is going to be a cup between what we have already figured out, which is the set that has B inside a tuple by itself, and also a set that has C inside a tuple by itself. Alright. Nope, it doesn't like that. And it has to do with me probably using, I thought I was using backslash. Oh, that's a square bracket, not a brace. That's why I didn't like it. There we go. Okay, so I'm gonna pause here and see if you guys are okay with this. Essentially, omega 1 BC becomes the union of the set that has B inside the tuple and the set that has C inside the tuple, because that is how we figure out the components of omega 1 of BC. So are we okay with this notation? Okay, so we have a few people saying yes and okay. But I just want to make sure that everybody is okay, because this class doesn't have just 2 students. So I gotta, and 3. Okay, very good. Alright, so if this is okay, then we're gonna figure this out. Okay, so now we're trying to figure out, okay, what exactly is this? Okay, so we'll first perform the union. Okay, and so this is going to look a little bit long. It makes me think whether I should continue to use just the $sign, or whether I should use a line, which allows me to use a multi-line setup. Well, I suppose we can just do it this way. So instead of complicating it any further, we'll just go ahead and do it this way. And for some reason, I cannot type in this window, so I'm gonna try it one more time. There we go. And the $sign is gone. It's supposed to be here. Okay, so now this becomes the set of A Cartesian product with. So now we're trying to make a union of these two. Now since those are definitely unique elements, so now we have B in the tuple as one element, and then we have C in the tuple as another element. And let me press the enter key so that you guys can see what we have at this point, and see if you agree with this is what we should end up with at this point. I'm just working out the expression step by step, but I do want to make sure that we are okay with each step before we move on to the next one. Okay, yeah, the top level is not going to be that complicated, so when we get to it, we'll get to it. Alright, so if this is okay, then we're gonna extend it one last time. So this time we are actually going to do the Cartesian product. So let me see if let me type here. Yep, okay, I can still type. So now we have the Cartesian product between A and B, and then between A and C. So we end up with AB in the tuple, and then AC in another tuple, and that becomes the actual result. And I mistyped something, and that's why it's not showing it. Yep, the expression is getting just a little bit lengthy. And let me double check, what did I input incorrectly? Backslash, open brace, backslash, close brace. That should be okay. Maybe it's just too long to display. That's my guess. But it doesn't do us any good, because if you cannot see it, it doesn't do us any good. Let me see if I can put a line feed, force a line feed in here. There we go. Okay. So are we good so far? Alright, so we got Victor saying, shouldn't there be another set of parentheses around B and C? We are collapsing. We are basically saying there's no structure. You cannot have nested tuples inside the tuple. So we are flattening, tuples so that they becomes a single level tuple. That's all. So Victor is correct. Okay, technically speaking, if we are allowed to use a hierarchical tuple, then it would be A, comma, and then B in a tuple by itself, and then the entire thing in a tuple. But since I said earlier that we cannot have hierarchical tuples, and because this basically has the same question, because otherwise we should have a tuple with B as the first item and then an empty tuple as the second item. But we don't, because we do not. We are basically saying we don't want to have hierarchical tuples. So does that answer Victor's question? All right, cool. All right, so this is a fairly long derivation, but once we know how to work one out, the other one is going to be pretty simple, right? So because it's going to be the same kind of mechanism to do the whole thing. So the second one is going to end up as a set that has BA in one tuple and then BC in another tuple. Like so. So I'm skipping all the steps in between because mechanically they are the same. We are just using different symbols in between. Is that okay? Or do you guys want me to like really spell it out? Okay, so I'm guessing that yes, we can use this simplified version because mechanically we're basically repeating the same steps. Okay, cool. And then this one is about the same. So this one is going to be a set that has CA as one tuple and then CB as the other tuple. And there we go. Well, we're not quite done yet, okay? Because what we have done at this point is we have figured out what is omega 1, omega 1 of BC, omega 1 of AC, omega 1 of AB, and we have even figured out the Cartesian product between A, B, and C with their respective omega 1s. What we have not done is the union of this particular set and this particular set and this particular set here. So we're going to do the combining over here, and we'll say that this is now going to be the set that has AB, AC in it, unioned. Okay, we have a cub with the next one, which is BA, BC, and then union one more time with the set that has CA and CB in it. So let me just kind of stop. It's taking up too much space. It doesn't like it. It does not like it at all. Alright, so let me insert a line feed and see if... Nope, still too big. This is funny. I think you guys got the idea, right? I'm not sure how to do that. You would think it's easy, right? To stretch out a cell. But since it's auto-sizing by itself, it's not it's not going to be that easy. I might have to change the style, of the bubble first. Or we can go vertical, right? I mean, totally going vertical, like inserting a bunch of line feeds, or break up the lines. There we go. It just looks kind of funny, but I guess it still represents what it's supposed to be. So after the unions, we end up with a set that just have AB as a tuple, AC as a tuple, BA as a tuple, BC as a tuple, CA as a tuple, and CB as a tuple. So that is how the whole thing works out. So are we good so far? I mean, I'm not gonna give you the final result of unioning all of these sets because it's pretty obvious, because none of these three sets share a single element, so the union between these three sets is going to be just one gigantic set that has all the elements in it. Alright, so I'm not sure whether this, I have never presented this material using free plane. So this is the first time I do it. Does it work out okay, or is it confusing? Because I think in the past when I just type it out, it was actually kind of confusing because you can't really track down using these lines to figure out, how the components work out. Yeah, well, this is recursion. This is me, doing recursion. We just have a very funny name, for the function. It's called omega. One of the parameters, which is the number of trials, is it appears as a subscript instead of a parameter. And then we have the second argument being the actual set. So for all practical purposes, I just track down how to do recursion by hand. So it is recursion to answer uh, Aman's question. This is recursion. It's just that it's recursion using mathematical notations. So if you define, a representation of a set, if you define union operations, if you define Cartesian product, you can actually turn this into a script. Okay, JavaScript would be easy to do, for this sort of stuff. All right, so we got a few people typing. Can we do combinations this way as well? I don't completely understand that. Okay, so I'm assuming that is referring to combinations. Yeah, so so there are a few ways to look at this. Well, the next section talks about what to do when we are dealing with combinations, when ordering does not matter. So we'll get to that. We will get to that. And we still have some more questions coming through the text channel, so I'm gonna wait a little bit. Or not. Okay. So let's go ahead and take a look at the next section, which talks about how to generate combinations. So let me go back to the browser. There we go. So now the question is, what if ordering is not important, and we still want to look at all the outcomes of an experiment, except we don't care about the ordering. So we got a few ways to do this. Okay, you can look at the permutations, and then you can find all the duplicates in the permutations and combine all the duplicates into one single. You can still maintain as a tuple. You just have to find out which tuple is equivalent to which tuple, and then when you find the duplicates, you just remove those from the result. That's one way to do it. And then the other way to do it is to use this mechanism here. So we're going to use this notation. U subscript I of x represents the set of all possible combination outcomes of an experiment with I trials, and the set x, which is basically doing the same thing as t, represents the set of choices available to the first trial. So if you look at this notation, it is basically kind of the same thing as the omega I of t notation, except instead of uppercase omega, I have u, and then instead of using t, I have x here. So notation wise, it's a very minor change compared to before. Now the base case is when you have 0 trials. So u0 of x, whatever x is, doesn't really matter. This time looks a little bit different, okay? Because this time, instead of using an empty tuple as the only element of this particular set, we have an empty set. In other words, this is still me, saying, oh, okay, I came back empty-handed because I was not allowed to choose anything from the bag. But this time, the quote-unquote empty hand is no longer an empty tuple. Instead, it is an empty set, because in a set, ordering is not important. So that's why we use a set to represent a particular outcome when an experiment does not care about ordering. So is that okay? Does everybody understand why we have an empty set here, and then earlier when we talk about permutations, we have an empty tuple? Okay, very good. All right, so what about the recursive case? So the recursive case is when I is not 0, when I is greater than 0. So when I is greater than 0, then what we do is about the same thing. We have a big union here, and then we say, okay, for each element in this x here, let's calculate this thing here. And then once we calculate this thing, we'll do a union for every single case. So in many ways, it is kind of the same logic, except in this case, this notation looks kind of strange, okay? Because in this case, we are instead of using a Cartesian product, we are using a union here, and we are using a union with s, and the recursion is actually down here. The reason why we have a recursion down here is because we have to form a we basically have to form a union with every single result of this particular subproblem. I'm not sure whether you guys are following or not, but let me check the text channels to see if everybody is still following okay. So the outer loop is going to choose what e we want to work with, and then the inner loop is going to first compute u of I minus 1 x minus e, which is going to come back with a bunch of sets inside a single set, which is the outcome of the experiment that has I minus 1 trials, but the first trial now only has one fewer item to choose from. So I'm choosing every single one set within the solution here, because this solution is a set of sets. So I'm choosing each element, and I go like, okay, let's make a union between e and that thing, and then once we have all of these items, then we form one gigantic union of those things. What is S again? So S is basically a loop variable. It is going through every single element of u I minus 1, of x minus e, and then for each iteration of this big U notation, we look at that S, and then we just say, okay, let's make a union of that thing. Yes, an example would definitely help. Okay, so are we ready for another example where I am going to track down things by hand using mind map? Okay, all right. So this time I'm thinking about not using LaTeX because that just takes up a lot of time. So this time I'm going to use just regular typing without using LaTeX. So the mathematical symbol is not going to look nice anymore, but it's going to be a whole lot faster to type. All right, so let's switch back to my map, and we're going to make a new one. All right. So this is going to try to work out what is U2 of ABC. Okay, so we still have the same initial set, and this time we're figuring out the combinations or the outcomes where ordering is not important. So once again, it has three iterations or each subcases. So once again, the first subcase is when e equals to a, and then e equals to b. Oops. Double tapping again. And then we have e equals to c. But this time, let me zoom in because the text is kind of small the way it is right now. All right. So when e equals to a, we want to find out, okay, then what do we need to do? Okay, so we go back to the definition here. So once we have chosen a particular value for e, then we need to figure out this thing here. Okay, but before we can even do the union thing, the first thing we need to figure out is what is u I minus 1 of x minus e. So let's figure that out first. Okay. So with this one, we need to figure out what is u1. Oops. Okay. For this one, we need to figure out what is u1 of because A is chosen by the first trial already, so for the second trial, we only can have B and C left. So we have to figure this out first before we can do anything else. For the second iteration, when E is B, then we have to figure out what is U1 of AC. And then for the third iteration, this is going to be boring because this is something that we have seen already. Because we take C out of the bag already, we only got A and B left in the bag for the next trial. So at this point, this is pretty much the same stuff that we have done already using the big omega notation. So we are not going to do the crazy union thing until we can figure out what is U1, okay? U1 of BC, U1 of AC, and U1 of AB. So now we look at this one and we say, to figure out U1 of BC, we have two iterations because, E would bind to B and then E would bind to C. So now we have two additional iterations here, where the first one is E equals to B, and the second one is when E equals to C. And likewise, over here, it is kind of the same deal. Okay, I kept pressing the wrong key. I pressed the E end key instead of it has to do with this keyboard has the insert key as function plus end key because it's a laptop computer. Alright, so E equals to A for the first iteration, E equals to C for the second iteration, and then for this one we have E equals to A and then E equals to B. So are we still doing okay so far? This is pretty much a repetition of what we did earlier because the differences between a combination and a permutation has not come into play yet. Okay, very good. Now, this time, what do we need to figure out? Recursively, we have to recursively figure out what is U0 of, since we took B out, so we only have C left in this case. And then for this case, we have to figure out what is U0 of B. And then for this one, U0 of C. And for this one, I mean, I'm doing a bunch of work here that is totally it's not meaningful because U0 of whatever always give you a set of an empty set, but just for the sake of understanding how recursion works, I am completing all of these specific cases because this way it would be extremely clear how recursion works in this case. Alright. Yeah, this is very tedious. Extremely tedious. But it does show you, how we went from U2 and then to U1 and then down to U0. So U0 is very easy to figure out. I'm not even going to bother with another level of notes. So what we are going to do is to say, oh, okay, this one by definition is a set of an empty set. So is this one over here. Okay, so now we're going to go like, okay, that's pretty easy. And this one. And this one. So far there is no, there's nothing here that is different from before. But that's because we haven't combined these things yet. Okay, so now that we have U0, when we are trying to calculate U1, what are we going to do? Now, both of these are components of U1. Let's go back to the definition of how U is defined recursively. So U is defined recursively. Once we figure out what is U0, then what we're going to do is to say for each element in U0 of blah blah blah, we want to make a set where it is a union between whatever element we have chosen as an element, as a set, sorry, union with whatever U0 is returning. Okay, so now we want to be careful because now we have E as a factor, and we have already calculated u of 0 of stuff. Okay, so what we are doing here is so we have e and then we have this. So now we can work out the combination between these two. Okay, so now we want to work out b union. So I'm going to use uppercase U in this. I know it looks kind of confusing because U is the name of the function too, but I think by context it is fairly understandable. This is representing union. So we have B unioned with the empty set by itself, and that is just the set of B itself, and the same thing over here. So this time we have, let me double check. I think I might have missed one level of set. So, yep, I missed one level because I need to make a set out of a set of the element being chosen and an element out of U0 in this case. So I forgot one more level here. So we are looking at this, and that is just that. Now, why do we have a set inside a set? The reason is the outer set is representing the set of outcomes, and then the inner set is an outcome by itself, because when ordering is not important, an outcome is represented by a set, because in a set, ordering within the ordering of elements within a set is insignificant. So that is why it looks like this. Okay, so there we go, and you can probably guess the next one is going to be about the same. So I am just going to skip one step and say this ends up with a set of A in it, and then this one is going to be a set with a set that has C in it, and this one is going to be a set of a set that has A in it again, and then this one is going to be a set with B in it. Whew. Okay, so are we still doing okay? Let me go back to the algorithm and show you where we are, what we are doing at this point. We have just figured out this term here. And so now we have these components, and we need to kind of do another union with, let's see. Yeah, so we are completely done with this step here because U0 returns a set with only one single element in it. So we are done with that step. So now we go back one more step, and we are now ready to figure out what is U2 of A, B, and C. So when we try to figure out this step here, then we have to do the same thing, except this time, E is A. So okay, so I'm gonna work out the details over here. So this one, so now we are trying to figure out A union. Okay, the set of A in a set unioned with U1 of BC, what U1 and BC is returning, and that would just be the set of B. This is one of them, and then the other one is the set of A unioned with the set with only C in it. So when you look at this, this is now the set. So each one, the first one becomes AB in a set. The second one, okay, I got it wrong. Let's see. Double set, right? There you go. So this is the first result, and then the second result is AC in a set, and that set becomes an element of the outer set. So these are the two things coming out of when E equals to A. and we figure out what is U1 of BC, because U1 of BC turns out to be just the set of B in a set and then C in a set. So what the later part is trying to work out is, let me go back to the definition, is basically when E equals to A, what is this thing resolving to? That thing is resolving to the union of these two items here. So let me change the comma. Oh, okay. Let me change the comma to a union. There we go. And obviously, in this case, when we try to do a union of these two sets, now let me make sure that we understand the scope of what set we are talking about. So this is one set, and this is one set over here. Both sets only have one item in it, because the first set has one single element. Now that element turns out to be a set by itself that has two elements, but we cannot look into the set as an element. So when we look at AB as a set, and then we look at AC as a set, they are different. So as a result, the union between these two outer sets is really just a set with AB in the first set as an element by itself, and then AC as a set as an element by itself. So let me just kind of pause here and see if this part is okay. From the perspective of expanding U2, when E equals to A, we figure out what is U1 of BC. We found that U1 of BC is a set that has B in the set by itself and C in a set by itself. And then the first step we need to do is to do a union of what E is with each result coming from U1. So we union A with B, which ends up with the set of AB, and then we union A with C, which ends up with the set of AC, and then we union between those two, because that's what this union is about. So that union ends up with AB as a set and AC as a set as the elements of the outer set here. Alright, so let me pay some attention to the text channel. Yeah, so there's a little bit of nesting here, and that part can be confusing. And then we have a question of, do we have to change the comma in the previous step to U as well? You mean this comma over here? Is that what you're referring to? Or these commas over here? Two more steps. You mean this comma? When I use the union as an operator, it's because we are performing either this union or this union over here or this union over here. I'm not sure about which one is the next one. You mean here? Or here? How about a screenshot with something circled? Okay. And this is why I think a synchronous class is good. Because if this class was asynchronous, it would be impossible for you guys to go like, wait, hold on a second here. But when it's synchronous, at least you can take a screenshot right away, and then use Microsoft Paint to circle something and then attach it to the text channel. That makes it a little bit easier. The other way to do this is to have you guys to screen share, so I can see your screen. So that way, that's the other way to do it. I believe we can do it that way too. So. I am a big non-believer of asynchronous classes. Yeah, I'm not going to take row today. It's okay not to take row one day, I suppose. All right. Not sure why that would be important. Huh. Oh, wrong image. Yep, that's what I thought. Well, this is the best I can do when things are online. Even though this is still an online class, it is synchronous. Oh, okay, that works. That works out pretty good. Okay, so yeah, so this is coming from the first loop. Let me show you which loop we are talking about, and this is coming from the second loop. All right, because we are taking whatever E is, and then we are unioning with uh, the outcome, the result that is coming back from U1 in this case of BC. So this union, okay, let me go back to the spreadsheet here. I mean the definition here. So this union, this one over here. Okay, let me see if I can show it side by side. Give me a second here to try to rearrange things a little bit. I think we can. We just have to kind of control the visible space of things, and then we go back to here, and then we scroll this one over here. There we go. Okay, nice. So now we can. I cannot see the text channel anymore, by the way, because I have just covered everything on the screen at this point. So I will go back and check the text channel after explaining this. This union is this union over here. So let me say it one more time. This union between the A and B, because A is chosen as E over here. So this particular union here is this union here. So you might be asking, what about this one over here? That's because U1 of BC has two elements. So when I union between these two, okay, so this one, when I actually perform the union, it becomes, A as a set union with B as a set becomes AB as a set. So this AB is coming from carrying out this union over here. This AC is coming from the union between these two items over here. So the question is, what about this union? Where is that one coming from? This particular union is coming from this union here, because this union is saying for each element coming back from U1 of BC, do the following. And then whatever this becomes, union all of those things too, right? So this union, which is basically a loop union, is this union here. And after performing this union, which is this union over here, we end up with ABAC when E equals to A, which is basically the first iteration of the outermost big union. Okay, now after talking about all of these kind of confusing union operations, let me go back to the text channel and see what questions we have over there. Okay, I just have to rearrange things a little bit on the screen. There we go. Okay. Oh, okay, great. So no big surprises. Okay, very good. All right, so let me go back to here. So now, since we figure out this one is just ABAC, A is the element chosen by the first trial, and then for the second trial, we have two possibilities because we can choose B or C, right? And B by itself is a combination, C by itself is a combination. So AB becomes a combination, AB becomes a combination, AC becomes another combination if I choose A first from the first trial. Now, for this one, I'm not going to go through mechanically the same thing. I'm just going to jump all the way through to the result of, what if we choose B first from the first trial? What kind of combinations are we talking about? So this time we end up with AB as one combination, and then we have BC as the next combination. And then for this one, when C is the first element chosen, basically the element chosen by the first trial, then we end up with AC as a combination, and we also end up with BC as a combination. Alrighty, so we are almost there. So now what we have done is to work out the actual result for each iteration of the outermost union of U2 of ABC. Yes, I know how bad that sounds. So let me go back to the definition and show you what we are talking about here. So we have figured out what is U2 of ABC, but we have pieces at this point, because what we have done so far is to go through all the iterations and say, what if we choose A first? Then we have worked out this subcomponent completely. And then we say, what if B is chosen? Then we worked out this component completely, and then we also worked out what happens when C is chosen as the outcome of the first trial. So now we have all the pieces, and it's time to combine all of those pieces. Guess what? By unioning all of them together. So, getting back here, so what we're trying to do now is to make a gigantic union of this set here, and this set here, and this set over here. So, I'm not sure that FreePlane will let me type that kind of expression, so I'm going to do this in a text editor to be sure, because FreePlane appears to have some kind of constraint of how long of an expression I can use, or how long of a string I can use. So I'm just going to be safe and use a notepad for this purpose. Alright, so at this point we are just going to be doing a gigantic union. So I'm just going to copy and paste, and then we'll work it out. Okay, this is from the first iteration when E is A. So this is one thing we're going to union, and this thing here is the result when E equals to B. Okay, so we're going to put it here, and this is what happens when E equals to C. Okay, I know I forgot to select the end curly brace, so I'm going to type it here. Alright, so let me use this one here. This is from the first iteration when E equals A. This is from the second iteration when E equals B. And this is from the last iteration when E equals to C, when we are working on U2 of ABC. Alright? And we are unioning all of these components because that's what the definition is asking us to do. This big U here is corresponding to the union operations that we are currently trying to perform. So now we basically want to answer the question, what is it going to be? So we're going to do this one step at a time. Okay, we'll do the first union, and then we'll do the second union. In other words, I'm going to impose an order here, okay, just so that it is clear what we are doing. So I'm just going to put in the extra parentheses here. Even though union is actually associative, I am enforcing an order here just so that I can show you step by step, how to do this. Alright, so we are focusing only on this set here and this set over here. And we're basically saying, if we don't want to double count or double list elements. So the set of AB is common between these two, so as the result it only appears once. So AB as a set, as an element, can only occur once. AC is on one side, it's not on the other side. BC is on the other side but not on the first side. So those two we get to keep. So we have AC and BC. In other words, when I perform the unions step by step, if I perform this union first, then we end up with this set here. So we still have to union this particular set with the last one over here. So I'm going to copy and paste it over here. So we paste it over here. So now we look at this and go like, okay, what is that going to look like? AB is only on one side, so we'll count it in without any problem. AC is appearing on both sides, so we will only have it appear once over here. And then BC is the same thing. It appears on both sides, so it can only appear once as the element of the result of the union. So this is our answer. This is our answer. If you are given a bag that has A, B, and C in it, you're asked to choose two things out of it, but ordering is not important. You only have three possible outcomes for the entire experiment. You can get AB out of it, you can get AC out of it, or you can get BC out of it, because ordering is not important. So are we doing okay with the recursive definition thing? All right, very good. Now, you might be thinking, this is easy to do if we just use a script to do it. I know we are running out of time. It's close to 6 o'clock. But I will tell you this one thing. Even though a lot of programming languages such as JavaScript actually has a notion of a set, the problem is none of the scripting languages that I know of can compare a set to another set. In other words, if you're trying to perform a union operation like what we are trying to do here, when the scripting language encounters a set in a particular as an element of one set and another set which is supposed to be the same as this one over here in another set, when it performs the union operation, it would do a literal comparison between this set as an object with this set here as an object, which basically means if they have the same address in memory, it will be considered the same. But it doesn't even bother to go in to actually check what elements are in the set. So that's why, when you use a scripting language, I don't even care which scripting language you use, when you're trying to do the union operation, that requires a nested comparison of things inside the set, it doesn't work out naturally for most scripting languages. You basically have to implement your own union operation where you have to say, hey, if an element is a set itself and the other element is also a set itself, I cannot just compare the addresses of the sets. I actually have to drill in to find out what elements are in the set, each one being an element of the two sets that you're trying to perform the union operation. All right. So, yes, so on is correct that permutation results in a set of tuples and combination results in a set of sets. But that kind of makes sense, right? Because in a permutation, ordering is significant. And guess what one permutation is? One way of ordering chosen items. On the other hand, in a combination, the ordering doesn't matter. Okay, I just want to know whether something is chosen. I don't care in which trial that thing is chosen. I just need to know whether it was chosen in an experiment. So in that case, it is natural to use a set to represent an outcome when ordering is not important. So when we say ordering is not important, the outcome is called a combination. So that is correct. So let me see if there are any leftover questions. I'm done so far with the lecture. All right, excellent. That is good. Okay, I'm glad to hear when people say, things are clear at this point. I hope this also helps you with some of your other classes, such as CISP430, because you can use about the same approach. When you encounter recursive algorithms, you can use about the same approach to basically say, okay, we have a recursive case here. What is the parent problem? What subproblems is it breaking up into, and then work on the subproblems. When you figure out the solution of the subproblems, then you look at each sub-solution. You look at all the sub-solutions, and then you ask yourself, how do we combine all of these sub-solutions? You perform the combination of the sub-solutions. Now you have the solution to a larger problem before you do the recursive call. So this is a general approach that I personally used when I try to understand a recursive algorithm. It also works in the opposite direction. When I want to derive a recursive algorithm, I will think in this manner as well. I'm given a bigger problem. How can I process this bigger problem so it becomes a smaller problem of the same nature? And then for each sub-problem, I would take the solution, and then somehow by combining the solution of each subproblem, I end up with a solution of the bigger problem. So that's basically it's a way of thinking when we are dealing with things that are recursive in nature. And you'll be surprised how many things are actually recursive in nature. I can talk about that in the next class because we are out of time today. Alright, so I'll see you guys next Monday. I mean, this is my office hour right now, so if you have any further discussion you want to carry on, I'm here. I'm still online. But other than that, I'm going to end the lecture today. Have a nice weekend, everybody.